not going to give you any notes until the second part, okay? So this is just stuff that I came up with that I thought was important from chapter 2. It might be helpful. And I won't give you notes like every single day. I'll try to as much as I can. But, so this stuff, first thing, important stuff from chapter 2. Is that what we should call it? Important chapter 2 topics. Chapter 2 topics. And the first thing, I don't even think I have to talk about this very much, but was function notation. It's easier for me to write when I have lines on the page. Functions. Function notation, that just is this idea of f of x, which is the same as y, right? You know that? F of x is the same as y. And so if they say something like f of x equals 3x squared minus 7, then you should know that f of negative 3 is equal to, and don't forget to plug it into parentheses. So you would have like 3 times negative 3, like that, squared, minus 7, which comes out to be 20. Thank you. Okay, 20. Chase. Any questions on that? You need to do f of negative x. Could you do f of x plus 2? Could you do that? So if we were saying f of x plus 2, like that, you would plug in x plus 2, and then you would, you can plug in x plus 2 everywhere you would see an x. So that would look like 3 times x plus 2 quantity squared minus 7, and then you'd FOIL that out, multiply by 3 and all that. Right? You can do that. That's just function notation. So that's something in chapter 2. Okay? What else? Then we have domains, okay? Domains of functions. And I know you guys did this in algebra too, right? Domain, didn't you? Talk about domain? But it can get kind of confusing, especially if you have rational functions or you're just looking at graphs or something like that. So if I have something that looks like this, I could have used my graphing, like a parabola that looks like this, and say this is the point right here, 0, 1. What's the domain of that function? Domain? Anyone? Yes, Sam. That's the range. Yeah, so x is, so you would, I always forget what x is, all real numbers. I think they do like this, and they do this thing that looks like this, right? With the little, have you seen that before? That means all real numbers. Or you could just write, and they put it in a little parentheses, but you could just say all real numbers. Because I could plug, it seems like this thing goes on forever in the x direction. So I could kind of look left and right and see that. But the range, Sam was right on the range. Range is the possible y values, right? So they would say something like y is greater than or equal to what? 1. So that would be the range. So looking at a graph, you should be able to tell the domain and range of something. So I'm going to try to get a better graph. If I have a, watch this. Isn't that cool? Isn't that cool? Wow. See, I'm pretty good with this. I'm almost as good as Mr. Tolbert. Okay, because I heard he's really good with this thing. Okay, so anyway, if I have something that looks kind of like this, I don't know, and stops here, okay? And say this is 3, and this is -5, and there's a definite closed dot there, and let's make this one right here an open dot, right? Whoops. I don't know why it does that. I haven't figured that out yet. Oh. But let's put an open dot there at 3. What's the domain of that? Explain? Anyone? Easy. Where's x going from? -5 up to 3, right? And yeah, so you could write it like, yes, I heard you. That didn't work either. X is greater than or equal to -5, and x is less than 3. And I put that intentionally in open circle. Or you could write that in function, in interval notation with a -5 with a square bracket on that end and a 3 with a curvy bracket on that end, meaning it's not included. Yes?
Yes.
Good. Okay. Domain and range, and I think you can figure that out the rest of it. You know about odd and even functions? Odd and even. You know what odd and even? Do you know what odd and evens look like? We'll talk about that graphically as well as algebraically. So let me get a new piece of paper. So function. Let me see. Line tool. Sometimes I don't draw these perfectly straight. That's okay. So if a function is even, okay, it would be symmetrical about the x-axis, so you could have like a sideways parabola, okay? That would be an even function. Understand that? Yeah? No? Maybe? And on an even function, they kind of look like that. We'll talk about, first I'm just talking about the graphs. I'll talk about the equations of them. That's even, okay? And something that might be odd would be like a reflection about the y-axis. I talked about this already. So odd, let's change colors. And something like this. Would that be kind of like that? See how this is kind of symmetric if I rotate over here 180 degrees? So with an odd function, if I have a point like 2, 1 on this graph, what point would be over here? -2, -1, right? And with an even function, that's why, right, when to test for even and odd, I plug in -y and -x, and it comes out to be the same thing, then it is odd function, okay? An even function, if it has a point like 1, 3 up here, then it would have the point 1, -3 down here. Okay, so that's even and odd and what they look like and all that. That's easy, right? Now they talk about increasing and decreasing, and I'm gonna draw this picture here. Increasing, decreasing. Okay, so if you have a graph, let me try one more time. Draw a graph. Does that look straight? Straight now. Like that. And if I have a graph that looks like, it's hard for me to, I have to stand kind of direct from the front. But I have something like this. And I should have made it like that, and say this is 3, and this is 4, and this, even though it doesn't look like it, is 1, and right here is 0, and this here is -2. It's not to skip, and this is -3. And they say state the intervals on which where this function is increasing, and state the intervals on where this function is decreasing. Okay? Who can tell me where would it be increasing? I can do it. Increasing. In other words, where is it going uphill? Where is it going uphill? Go ahead there, Sam. Good. So it's increasing from here to here until you get to about this point. You see that? going uphill. So it's increasing from negative infinity, right, with a curvy bracket on it, up until 2, also with a curvy bracket on it, because we don't know right at negative, oh, it's not at 2, at negative 2. We don't know right at negative 2 whether it's increasing or decreasing. It looks like it's doing nothing right there. I mean, this isn't an exact graph. Where else is it increasing? Where, John? Okay, and very good. And 0, 2, 3 with curvy brackets on it again. Okay? Because at 0, 2, 3 it's going uphill. And I know I had something like this on the handout, and people always want to put the y values in here. Okay? So if this were like 2 here, and this were like negative 2 here or something, do not put the y values. When they say where is it increasing, where is it decreasing, you put the x values where it's going uphill. And then so this would be decreasing where? Where would be decreasing? Hannah? Negative 2, 2, 0, and then where else? And from 3 to perfect. Okay? 3 up to, it looks like it goes on forever. Any question on what increasing or decreasing means? Okay. We're not done yet, but I could pause. Okay? So we're going to talk here about the average rate of change. Okay? And the average rate of change is basically the slope of a line. And we talked about that in some of the review packets. Okay? And this idea of the average rate of change becomes very, very important when you get to calculus. Okay? Because in calculus they talk about the instantaneous rate of change. That's lots of applications to real life, believe it or not. Okay? So if I were talking about the average rate of change between 2 points on this curve, let's say from 1 to 2. So what I'm going to do, I'm going to take this problem, watch this. I'm going to take this problem, commercial, boom, boom. I can do this. And I'm going to make this bigger. Good. Wow. Look at me go. And I'm going to draw a line like this. Okay, and it's kind of hard to get it exact here, but say this is the point. This is x equals 1, and this is x equals 2, even though it's not really to scale. And the formula for finding the average rate of change, and another name for that is the slope of the secant line. Remember in geometry, the secant line was a line that cut through a circle. Remember that? So the slope of a secant line, and that's equal to f of x minus f of c over x minus c. How many of you have seen that before? Has anyone ever seen that before? Good. So all that is really the slope of this line between those 2 points. And the way you would find it from 1 to 2, I'm sorry, I don't have my function right here. What was that function again? 2x squared plus x? 2x cubed. So f of x equals 2x cubed plus x. Okay? And so all I do, f of x, in this, to start with, we call this point x, the furthest one away x, and we call this point c. Okay? So it doesn't really matter which order you go in, really, just like with slope, as long as you're consistent. But so f of 2, so f of 2 is 2 times 2 cubed plus 2, which gives you, is that 18? Yeah, 18, okay? And f of c, which I'm going to call f of 1, is equal to 2 times 1 cubed, which is 2, plus 1, is that 3? Yes? Okay, so on the top, what I have is f of x minus f of c, which is 18 minus 3. And on the bottom, I just have x, which is 2, minus 1, right? And I get 15 over 1, right? Which is just 15. Yes? Okay. Now, say I want to find the slope from 0 to 1, right? So let's do that really quick. So the slope, the average rate of change, which is also equal to the slope of the secant line. In other words, the slope of this curve right there, right? So f of 0 is just what? What's f of 0? 0. And we already know f of 1, right? So that would be 3 minus 1 over, right? Because f of 1 is 3. Oh, wrong. Sorry, 3 minus 0, right? Is f of 0 over 1 minus 0, which is 3 over 1, which is just 3. So in other words, the slope of this curve from here to here is 3, whatever those units happen to be, and the slope of this right here is 15. What do you think would happen to the slope as I went on? It increases. Anyone know why that might be important? Say this were a rocket blasting off, okay? And this is like distance, so, or this is like distance over here, and this is like time over there. What would the slope of that line represent? The speed of the rocket blasting off. So that's like how they tell, I don't know if that's really how they tell, but that's one way they can tell how fast things are moving in space, you know, like aerospace engineers and stuff like that. Well, this rocket moved from here to here in that many seconds, and by the change in the speed, right, they can figure out how fast it's accelerating, they can predict when it will get to somewhere else, and something like that. And that's what calculus deals with. That's just, now we're just dealing with it as rate of change, average rate of change. When you do calculus, you find the rate of change exactly at one point. So you find the speed at that point and the speed at that point. Or it might relate to like a business thing, like how fast are my sales changing or something like that if you're in business. So there are like real applications for it. Anyway, I'm not going to do the next one. What's going to happen if I hit this button? Okay, don't. Oh, that's okay. That's what I wanted to do. So I'm not going to do this one. It's just another function. It's the same idea. Then you can figure that out. Okay, even and odd functions. Good. The rules are, okay, if f of x equals f of negative x, then it's even. And if f of negative x equals negative f of x is odd. In other words, plug in negative x or x. And if the function doesn't change, then it's even. For instance, in this one, 4 plus negative x, you got to put it in parentheses, squared, over 1 plus negative x raised to the 4th. What happens when I do that? It doesn't change, right? Because this is even, so something raised to the same power, you're going to get that's equal to 4 plus x squared over 1 plus x to the 4th, which is the same as what I started with over there. So that is even. Right? An odd function, you plug in negative y and negative x. Or this is y, okay? Or excuse me, this is y, and this is x. So if I'm going to look at this function, and this is an odd function, g of x is like y. So I'm going to rewrite this as y equals x cubed minus 4x. And then what I'm going to do, I'm going to change colors to show you. And so I'm going to plug in a negative y for this y. And I'm going to plug in a negative x for this x. Okay? And I'm going to plug in a negative x for this x. Okay? And then when I simplify this, I get negative y. What happens when I cube something with a negative? It's still negative x cubed. Okay? What's this going to end up being? Plus 4x. But you say, wait a minute, that's not the same as what I started with. Right? Is that the same as that? It will be. Watch. If I take this whole thing and I multiply it by a green number, negative 1, negative 1 times this changes this into a y. Negative 1 times this changes this into a positive x2. And then negative 1 times this changes this into negative 4x. Is this the same as this? Yes. Therefore, this function is odd. And if I were to graph that function real quick, it would be, let's see, it has 0x, I don't know, x minus 4, I think at 4, and at 0, and I think this would look something, I don't know, like, maybe like that? Probably not. But it would go up and down, it would be symmetric about the order, okay? Last one, what do you think this is, even or odd? Or neither?
Neither.
You know what? I think this one is, I think it's odd, actually. Because if I plug in negative y in there, negative x over 1 plus negative x squared, okay, what I end up getting is, how do I move over? I'm going to run out of room. I got to figure that out. Oh well. But if I do this, I get, I'm going to continue over here. Negative y equals negative x over 1 plus x squared, right? And then if I multiply through by negative 1 again, I just multiply through the top. I don't multiply the top and bottom of this fraction by negative 1, right? What? No. Because, why not? Say I have like, what do I want to do? Let me, 3 equals negative 6 over negative 2. Would you agree with that? Right? Okay. So if I multiply this by negative 1, or I'm going to try, right? I get negative 3 equals, I don't multiply both of these, right? Because that'd change it into a positive, right? So I just multiply one thing, because this is a quantity in itself, okay? So I can make my eraser bigger too. So when I multiply that through by negative 1, I end up getting y equals positive x over 1 plus x squared, and therefore that function is odd as well. And if you were to graph this, I'm not exactly sure, but I think you get something that kind of looks like asymptote there, and I'm not sure what it looks like, but I think something like this. So you could graph it on your graphing calculator. Yes, sir?
So if you see the equation,
people always, they say, well, what ones are neither? So anything that has like even and odd. So if you had something like y equals x squared minus x, right? That's an example of something that would be neither. Because if I plug in negative x squared, it's going to change it, right? Or negative x in there is going to change it. If I make them both negative, because this has an even number and this has an odd number. If both of these would be even, then it would be an even function. But if one's even and one's odd, then it's not. Okay? Okay, so